Hello everyone. So let's talk about the estimation of parameters. Previously I showed you how we can use the distribution, sampling distribution, and then before you start this lesson, try to take a look at the sampling distribution. We will be using much of those equations, distribution, the critical values, all of those in the estimation of parameters. So in the estimation of parameters, you will see that we have estimation of points and estimation of intervals. So if we are trying to find a sample statistics that's used for estimating a parameter, then we call it a point estimate. That means you are going to get one value. The examples I gave you previously, it's about, let's say we have a z statistics value. Using that statistic value, you can go to the, you can open the z table, and in the z table you will see that for that specific value, what would be the probability under the curve, or you can find the above the curve. Just take out the let's say if you want to find the above area, then you have to say 1 minus of the probability. Similarly, we can do it for t distribution as well, but then again, whenever we have chi-square or let's say f distribution, then they are not symmetrical. That means not bell shape, it's skewed on the right side, so we have to consider the other method of finding the critical values. Let's talk about the point estimate. So in the point estimate, since I mentioned to you that we are going to estimate a population parameter, so let's say if we are interested to find what might be the population parameter, that let's say what might be the population mean in a population. If we have, let's say in a forested area, in that forest area, what might be the population mean? And then since we don't have the population data set, then we use sample. Using a sample, we can find the mean. Mean is the statistic here, and then we can say that it might be in the population, it might be this value. So that's why we use for the sample, we use x bar as the sample mean, and then mu is the population mean. That's what we are trying to estimate, that we are trying to make inference about. Similarly, for proportion, we are going to use the p hat is the proportion. This is the point estimate for proportion, the population proportion. And then similarly for variance, the sample variance, this is the point estimate for the population variance. So many times you will see that people are talking about unbiased estimator. What is that? So I showed you in the sampling distribution, whenever we try to take, let's say we are taking samples many times, then you will see that if you considerably repeat that many times, then you will see that the mean of the mean is actually the same as the population mean. That means there is not much error involved in that. If you repeat that, let's say 10,000 or 20,000 times. If the sample size is larger, then you don't need to repeat that that many times. But in case of the sample variance, what happens is that even if you repeat that many times, you will see that it actually gets reduced for the mean. And then that's why sometimes we say that it's a biased estimate of sigma square. That means there are some errors involved because it's not exactly same as what we have in the population. So you can see whenever we say an estimator is an unbiased estimator, then it's more efficient, and then that has the smallest variance. That means it's not varying that much. Let's say we take the mean many times using repeated samples for many times, then we get smaller variance. So for the estimation of intervals, it's extremely easy to find, since you already learned how you can find the critical values, how you can find the standard deviation, that's what we need, because using those two we can find, for any statistic we can find what would be the interval. So that's why let me go a little bit later, I'll talk about those. So you can see that we mentioned what would be the point estimate. Let's say, let me draw that. So let's say we from a sample we found a mean using a sample, then plus minus of the critical value. Let's say we use t, or maybe we use z, based on the sample size or based on the whether the variance is known or not. Let's say we use t, and then t critical value, and then the v is the degrees of freedom. And we also need to think about, is it the upper area or lower area. So let's say we are using y2, and then you have to multiply it by the standard deviation. That means the standard deviation, what you find for that statistic. Okay, so that means mean to mean, what's the variation we have, critical value from the table, and then what's the statistics we are talking about. So why we are doing that? We are doing it because we will find the two values. One is the upper value, one is the lower value. That means it will give us confidence interval in our distribution. So we need to think about, whenever we are creating the confidence interval, then within the level of significance, what are the probability we are getting. So let me draw that. So let's say we are trying to find the confidence interval for mean. Then it follows the z or t depending on how many samples you have, and depending on whether we have the variance for the population or not. Let's say we have the variance for the population and the sample size is large, and then we find that if we repeat the sampling process many times, then you will see that this is actually the mean of those mean is actually the population mean. So we want to find that since we are repeating that many times, and then how many times, let's say how many times we get within a certain interval. Let's say 95% time we find the mean within this interval. That means 95% sure that the mean that we are getting, that means we are repeating, we will get within this interval. The rest will be 0.05 or 5%. So 5% times, if we repeat the sampling process many times, then 5% times you will see that it's lowered this value or above this value. So that means this small area, this is small area, I didn't write it, the graph I created doesn't look like it's small, it's a small area. So the 5% will go onto this. That means the you can say that 2.5% here, since this is a Bell-shaped curve, 2.5% will be on the other area. So what we want to find is that what is the region, that means the 95% time we can say that it will fall within an interval. So interval means there will be a lower value and there will be an upper value. What are those values? That's what we want to find in the confidence interval. Not always we will have this level of significance or confidence level, Sometimes if it changes, let's say it's actually 97%, then you have to consider that 3% will be on these two regions. That means 1.5% in both regions. Basically, if it is not mentioned, you can say that 95%, you can find the confidence interval for the 95%, or if it is 99%, 99% confident, you can confidently say that the mean will fall within an interval. So right now I want to show you how we can find these two values. Okay, that's what my interest is. For the, you have to think about the, are we talking about mean, variance, or ratio, or what is it, what kind of distribution it follows. Based on that, we can find the confidence interval. So you can see that for confidence interval for mean, if we know the variance, population variance, and if the sample size is large, then we can say that falls within the, we can say that it will actually follow the normal distribution. Then we can easily find using the Z distribution. So in the Z distribution, we basically need two values: the Z critical value, Z critical value for that specific level of significance, and then the sigma divided by root over n. That means that's the standard error for the mean. These are the two values we need to find. If we know these two values, we can easily find the confidence interval. So let's say using a sample, we already have a mean. Let's say we are talking about 95% confidence interval. Then 95% confidence interval, the Z value, like I said, we need the Z value. Z value is 1.96. If you look at the table, then you will find that, let's say, the 95% confidence interval, that means the middle area is 95%. That means in the Z table, you can go and take a look at for the value 0.975, or you can find the value for 0.025. In both cases, you will see that the critical value is 1.96, negative 1.96, positive 1.96. My writing is pretty bad since I'm using the clicker. Okay, so that's what we did. We just added the these from the sample was the mean we found plus minus the critical value. So you can see critical value and the standard error. We did the same, positive and negative. Then we found, you will find two values. Then you can say that within 95% interval, the mean interval is that, and then we can expect that 95% values, the mean will fall within this region. Similarly, you can find for other confidence interval. All you need to do is to find the, if you change the confidence level, all you need to change is this critical value. And for T, you know, it follows the, if it follows the T distribution, for these two regions, the population parameter is not known. This is the standard deviation or variance is not known, and then sample size is small. Then we have to use the T distribution. Using the T table, you can find the T value, and then you can see that the standard deviation will use the sample standard deviation divided by the square root of n. So the T distribution, you know, the critical value, you have to use the degrees of freedom. Degrees of freedom, you can use the sample size minus 1. Then you can go to the T table and find the T critical value. Basically, we are using this equation to find the confidence interval. So basically for T and Z, you will see that this part is changing. That means you can see that the means whenever we don't know the population variance, we have to use the sample variance, and then we have to use the T critical value. Let's talk about the how we can find the sample size. So it says the given error, so that means whenever we are talking about the sampling error, then we have to consider that since we are repeating the process many times, maybe we could have some errors in there. So that means after we get the population, then we will have an idea. But whenever we don't have the population value, we have the sample. Since we are taking samples many times, and then each time it might be different, how far it's varying from the population value, that's where our sampling error is coming from. Since we are not using the population, since we are using these sample values, that's where our error can be producing. Okay, so we can actually refer the sampling error and then define that using E for the Z statistic, for the mean, you can say that. Then what happens is that since we have the sampling error and then we have the error part, we can actually rearrange this equation, and then we can actually take n on this side, and then we can find what would be the sample size. So all you need to do is to take the square, and then if you take the square on both sides and then take n on this side, then you will see that we have the error in the denominator, and then we have the critical values and variance. So based on why we are doing that, based on how much error you will allow, so that means the mean would be somewhere here, right? And then we allowed some space, some errors, let's say for clearing the confidence interval. We say that we will allow this much. After this cutoff point, we are not allowing, we are saying that anything goes beyond, that's not the true value. That means how much you will allow. Would you allow this much, or would you allow more? So based on that, then you can find the sample size. That's why we try to rearrange them. And then this is for Z, but then again, if we do not have the population variance, if we do not if the sample size, let's say, we do not know, then the what we can do, we can say that it follows T distribution, T test, and then we can replace them with T statistic value, and then the T critical value, and then the sample variance, sample standard deviation, and the sample size. So if we again rearrange them, then we will find that how much we will be actually allowing the error. Based on that, we can define what would be the sample size. So for the confidence limit for the difference between two means, it's exactly similar to one population. So you can see that we have to take the difference between them, and then the pooled estimate. This is the pooled variance, using the two populations variance and the sample size. Then we can use the Z. Since the population variance is known, then we can find what might be the interval. The only thing you have to be careful is that what's the Z value you are inserting. So let's say I'm talking about 95% confidence interval. Then from the T table, you have to find what would be the value for 0.975 or maybe 0.025. If the level of significance changes, let's say the level of significance is previously I talked about 0.05 or 5%, either way it's fine, or it would be 0.01, maybe 1%. So based on that, you have to find the critical value. If it is 0.01, that means we are talking about 99% confidence interval. If it is 0.05 level of significance, we are talking about 95% confidence level. Okay. So if you go to the T table, then you can find what would be the value for 95%. You have to find the 975. For 99%, let me show you what you have to find from the Z. Okay, so let's actually draw first for 99% confidence interval. What are the values you need to find? So the 99% confidence interval, 99 is in the middle, 99%. The 1% will go here and here. That means this 1% we have to divide by 2. If we divide 1%, that means divide by 2, the 0.5%, 0.5% on both sides. That means 0.005, right? If we are not using percentage. So this critical region, it will be 99, 0.99 plus 0.005. So that means this one is 0.005, this one is 0.995. So all we need to do is to go to the Z table. In the Z table, you can see that for 995, let's find 995. There is no exactly 995, but we can say that it will be in between these two. In between these two, it will be 2.5, 7 or 8. So let's say 2.58. So that means the both side, you can say that it will be negative 2.58 and positive 2.58. So that means you can find the critical value and then you can insert that. Let me clear. Okay. So all we were trying to find is that based on the objective, then for mean, difference between two means, add the sample difference, add the pooled standard deviation, and then the Z critical values. Then you will find the two intervals. That means the upper and lower confidence interval. You will find them. If they are greater than 30, but the variances are not known, in that case we can also use Z, similarly what we used before. But if they both are less than 30 and then we do not know them, the population variance, then we have to use the T statistics, and then you have to change the values. Okay. The error part you have to change every time, and then for the T, you again can go back to the T table and find the T critical values. Okay. I showed you actually all these before, the pool variance, and then how you can add that. So that's the same thing we are doing in here. Or you can write down everything on the cheat sheet, what we will be using for two population, and then if we are trying to find the difference between the two means and then what's their confidence interval, then you can use that. And then previously I showed you all these. So it's for the pair data set, so we use d bar, if you remember them in the previous lesson. Then you can use the d bar, and then what's the standard deviation was the critical value. You can easily plug in these two and find the confidence interval. Now we will learn how we can find the confidence limits for proportion. Previously we used the Z distribution for proportion. We will use the same. So the sample proportion plus minus the Z value from the critical table we have, and then the standard deviation of the proportion. We can just add them and then we can find it. So for the finding the sample size for a given error, that means if we are given what might be the sampling error that we might consider, then we can easily find what would be the sample size. To find the sample size, you can easily actually use the Z or T depending on what's the distribution you are using. If the error is given, how much error we are considering, then what's the proportion, the success and failure, or the proportion that we are considering as true or as false, you can add them and then you can find what might be the sample size. So for the confidence interval for difference between two proportion, it's again for use the Z distribution, and then you can use the difference there, the combined variance, you can find that. Similarly for confidence interval for the variance, then you know we only need two items. One is the sample variance, and then all you need to do is that add the critical value. So for the critical value you have to use the level of significance by 2 and then the degrees of freedom, but for the upper region you have to use the other region. So you can see that. So for variance, for ratio of variance, you can use the ratio, but then again you have to consider, since I told you previously in the previous lesson, that we have to use the reciprocal, because we are going to use the chi-square, and chi-square is not symmetrical, that's why. So one more thing I want to mention to you is that, let's say you want to try finding the sample size, then you need to consider that if the sample size you get is already larger than 30, then you can stop there, and then it can be let's say you can do the iterative process. Let's say at first you use the for T, actually let me see whether I can find that. Okay, so for T distribution, let's say we are trying to find what might be the sample size. At first you use the T level of significance for really large sample size, let's say infinite. Using that infinite, then you can use the T value and then sample size and then how much error we mentioned, and then you can find the value. The next time what you have to do is that when you find the sample size, if the sample size is small, then you can again find using that sample size you can find the T value. Let me actually draw that. So let's say you found value 10. So next time you have to use that value 10. Everything will be same, s square and then e square, those will be the same next time. Only thing is that T value for the previous sample size 10, you have to find what would be the sample size using this 10 minus 1 degrees of freedom. So that means T value will keep changing. So if you see that you are keep doing, let's say you found n1, n2 and then n3 and then blah blah blah, you can go up to n15 or let's say n16. Every time you are changing the T value. If you find the T at the 15th or 16th step, if you find the sample size is exactly the same, then you can stop there. Or if you find that sample size is more than 30, then you don't need to do the work again. That's how you can find the what might be the sample size we have to use. Okay, so that's it for today. Thank you.